Um, if you were to take a look at this, the salami problem, okay, let's take a look. Here, I have 11 kilogram salami. That's pretty huge, actually. 11 kilograms. It's like 25 pounds of salami in figure A is supported by a cord that runs to a spring scale, which is supported by another cord from the ceiling. What is the reading on the scale? Now, if the scale is reading, mass in kilograms, that's going to be obvious, right? If it measures the weight of it, then it should be measuring in newtons, okay? So let's take a look what it would be like if it were to be measured in weight, okay? So we know by looking at this for part A, we're going to have Fg going this way, and we will have tension going up that way, right? So we could say tension A here. Well, this tension A should be exactly the same value as your Fg, which is equal to mg, right? So tension A is equal to Fg, which is equal to 11 times 9.8. So your tension A is equal to 107.8 newtons. Now, if it measures in kilograms, right, where they calibrate this, then you should just read 11 kilograms. But if it measures weight, then it should be measuring 107.8 newtons. Now, if we take a look at this, right, so this was that, right, then here we're going to assume the scale is massless, so it doesn't have any mass. Very ideal scale. Now, what's going on? Well, this thing is being pulled down by TA, right? And it should read exactly that, just TA, okay? And obviously, this scale is held up by, right, another tension going this way, TB, and this is, again, TB going down this way, which should equal to each other, so they should cancel out, right? So this scale should read TA, so that should be 107.8 newtons is what it should read. Okay? Now, what about part B? In the figure B, the salami is supported by a cord that runs around the pulley to a scale, right? The opposite end of the scale is attached by a cord to the wall. Now, if I were to grab this part right here, this part of the string, right, and cut this off from the wall, and if I were to go like this, what should the scale read? It should be exactly the same as this, right? This pulley is really not doing anything except it's just changing the direction of the tension, but it's not going to really affect the magnitude of that tension whatsoever, okay? So whether I have this thing up like this with the scale here, okay, or whether I have it here like this with the scale at this angle, right, or here, it really doesn't matter what angle this thing is because this pulley is just actually redirecting the tension's direction. But so this scale should read exactly the same as 107.8 newtons. Okay, so this should also read 107.8 newtons. Then comes to trouble right here. Now, people would say, well, this is obvious. You got two salamis, so this scale should read twice as this, so it should be around like, 215.6. And the answer is no, it's not 215.6. Some may say, well, shouldn't they just sort of cancel each other out? So it should read 0. That's even bigger no. Because this thing is supporting two salamis. Okay? Now, how do I explain it? I would usually show this in demonstration because I would actually hang masses on the other side with this whole setup. And people would be like, oh, wow, that's so cool. Well, let's say I grab this string right here and cut this off. That's nothing different than this setup right here, right? So it should read 107.8. Similarly, if I were to grab this string and cut this off, what would it read? It should read 107.8 newtons. So what's the difference between me holding this string versus same amount of force that I should be holding this thing by another weight? So this weight of this salami's weight is supporting this salami, and this salami's weight is supporting this salami's weight. So this scale should read exactly 107.8 newtons. I hope that's understood. All right. So popular wrong answer would be 215.6. And then the second popular wrong answer would be 0. But the correct answer is 107.8 newtons. All right, I hope that's explained enough. All right. Any questions before I move on? Can you guys hear me? Hello?
Yeah, I can hear you.
Thank you. Okay. Because last class, like I got dropped. So, all right. Now comes some couple systems here, and this is pretty important concept as well. Okay. So I have 3 blocks that are connected, as shown in figure below, as a horizontal frictionless table, and pulled to the right with force of tension 3 is equal to 65 newtons. If M1 is 12 kilograms, so this is 12 kilograms, M2 is 24 kilograms, M3 is 31 kilograms, okay? Calculate A, the acceleration of the whole system. And then for part B, calculate the tension 1 and tension 2. So if I were to look at this tension 1 is connected by a cord. Let's say this cord is like really infinitesimally small, like size of an atom. So let's say, you could combine them, right? So don't let the length of the rope really confuse you about the magnitude of the tension, right? So I could actually combine them. I could combine them and look at this whole system as one unit pulled by only tension 3. Okay? So let's redraw this in the, like, you know, in the different side here. So here's my M1. And this M1, okay, will be pulled by, let's say, tension 1. And then we have M2. This M2 will be connected to my M1, so it'll be pulled back with tension 1. And it'll be pulled by tension 2 going this way. And then M3 will be pulled by tension 3. And it will be pulled back by tension 2. Okay? So at first, what I can do is I can actually look at this whole system as one, like this. This whole system as one. This whole system is pulled only by tension 3. Okay? So if I were to look at the whole system as force, net force external, right, is equal to, right, mass total, right, times the acceleration of the system. This mass total is really nothing more than just, you know, M1 plus M2 plus M3, okay? Times acceleration of the system. Right? So M1 plus M2 plus M3. Well, how many forces are acting on this externally? I mean, if you didn't want to use external force, you could use all the forces if you want to, and then this will be positive, negative, positive, negative, positive, right? You could have done that too, but if I were to look at this as a whole system, there's only one force pulling on that system, and that's tension 3. So if I set these two equal to each other, right? So saying, you know, M1 plus M2 plus M3 times A of the system is equal to, right, tension 3. Right? So here's my M1. It should be M3, sorry. So M3, and this is my M2, and this is my M1. Right? Let's plug in some values. Okay, so here I have 12 plus 24 plus 31 times A system is equal to tension 3, which is 65 newtons. So my acceleration of the whole system is equal to 0.97 meters per second squared. Now this acceleration is for mass 1, mass 2, and mass 3. All right, so the acceleration for mass 1 is 0.97. Acceleration for mass 2 is 0.97. Acceleration for mass 3, 0.97 in the horizontal direction. So this is basically, for part A, use it as coupled system. Now for part B. Let's uncouple this, okay, for part B. So if we uncouple this and look at it individually, let's take a look at just M1 here. So here, if I look at just M1, okay, what's going on? There's only one force in the horizontal direction, and that's tension 1. Obviously, there's going to be, FG1 and then F normal 1, right, etc. But they're going to cancel each other out. But the horizontally, there's only one force, and that's tension 1. So I can say now sum of all force 1 is equal to M1A, and this A is the A system, okay? And then sum of all force 1, there's only one force, and that's tension 1. So I can say, right, M1A is equal to T1. They're both positives. So M1, 12, times A, which is 0.97, is equal to tension 1. And my tension 1 is equal to 11.64 newtons. All right. Well, what about the second one? Right? What about this one right here, mass 2? The tension 2 can be calculated using either mass 2 or mass 3 because they both have tension 2 involved in it. So here, let's take a look at mass 2 first, if you want, and then I'll do mass 3 later too. So this one obviously has 4 forces acting on it, and that's basically Fg2, right? F normal 2, and we have tension 2, right? And we have tension 1 going this way. So we're not worried about the vertical forces because they'll basically cancel out to 0, and then F normal 2 is equal to Fg2. However, if we were to look at horizontal direction, the sum of all force 2 is equal to M2 A system again, right? And let's take a look at all the forces acting on mass 2 horizontally. That would be tension 2 and tension 1, right? So M2A is equal to tension 2, I'm going to call that positive. Tension 1 in this case is negative. We already know what that is. We calculate it to be 11.64. Right? So M2A, which is 24 times 0.97 is equal to tension 2 minus 11.64. So if you calculate this thing out, your tension 2 comes out to 34.93 newtons as my tension 2. Okay. Well, you don't have to just do it this way. You could have done actually using mass 3 if you want to do it that way, right? Let's see how that would look if we were to use mass 3 instead of mass 2. Hopefully we should get the exact same answer because, it's math. So here is my mass 3. Mass 3 has obviously, right, we've got Fn3, and then we've got Fg3, we have tension 3, And we have tension 2. Again, vertical forces, we're not really worried about them, right? Because they're going to cancel out to 0. So Fn3 is equal to Fg3. However, for the horizontal motion, sum of all force 3 is equal to M3 A system. Therefore, sum of all force 3 is equal to, here I have tension 3 plus tension 2, right? So there are two forces horizontally. So if I set them equal to each other, so M3A is equal to tension 3 positive, tension 2 negative, and we already know T3 because it's given to us in our problem to be 65 newtons. So let's plug in all the values that we know. M3, 31 times 0.97 is equal to 65 minus T2. Well, we could solve for T2 now. It is equal to 65 minus this John, right? Which is 34.93 again. Same thing. All right, so you could use it any way. Any questions? All right, good. Moving on. This again is a very important conceptual problem here, okay? So two blocks are in contact on a frictionless table. A horizontal force is applied to one block as shown in the figure. So here we have block 1, and force is applied onto block 1 towards the right, okay? And the mass 1 is 2.3 kilograms. Mass 2 is 1.2 kilograms. And the force being applied is 3.2 newtons. Find the contact, right, force between the blocks. So if I were to place a quantum observer between these two blocks, right? This quantum observer is in between, observing what's going on between the two. All right? This quantum observer has plenty of space between these two blocks and definitely can observe what's going on. All right? So let's take a look at block mass 1. Okay? And let's take a look at what forces are acting on mass 1. Obviously, there's going to be Fg1, right? And then there's F normal 1 this way. However, the force being applied horizontally this way, right? F, which is 3.2 newtons. Now, obviously, I exaggerated this drawing right here because these should be a lot bigger, but I'm not going to worry about the vertical ones. And then, here's the important one. There's a second normal force applied onto block 1 in the x direction, right, by block 2. So this one is F normal in the x direction, right, on 1 by 2. Okay? Now let's take a look at mass 2. Okay? Mass 2 is accelerating that way because the force applied onto mass 2 is by mass 1. And that force is the exact same force as this in the opposite direction. This action-reaction pair right here. So this Fnx on 2 by 1. That's the force that's making M2 accelerate with the same system acceleration. Okay? So let's think about finding the system acceleration of the whole system, right? So couple them together. As one, right, to get a system. And we're going to consider this direction to be positive in our case. So sum of all forces is equal to M total, right, times a system, right? This M total obviously is equal to M1 plus M2 times a system, right? And then sum of all net force is equal to, there's only one force, and that's the force push, right? So if I set them equal to each other, I should get M1 plus M2 times a system is equal to F. So if I plug in the values, right, my acceleration of the system is equal to F, which is 3.2 newtons, over 2.3 plus 1.2. And that comes out to 0.914 meters per second squared. So this is the acceleration of both blocks. Okay? So now let's take a look at what's going on individually. Well, if I were to just take a look at just M2 and solve for this, it's easy. Okay? So let's take a look at that right here. Sum of all force 2 is equal to M2 a system. Now, sum of all force 2 is equal to just Fnx. Right? Don't forget there are two F normals here, right? There's one going like this, there's Fg2, and then there's Fn2, right? And then this Fnx is the one we're looking at. Therefore, M2A system is equal to Fnx. So what's my Fnx? My Fnx is equal to just M2 times acceleration of 0.94914. So that is equal to 1.1 newtons. All right, so Fnx is equal to 1.1 newtons. Well, let's see if this is true if I work with this. Let's say, all right, well, let's say I don't want to work with M2. I want to work with M1. Well, that's fine. So we could say, all right, let's do that. So here, let's take a look at what happens if we work with M1 instead, right? Sum of all forces again, sum of all forces 1 is equal to M1A system. Okay. Then sum of all force 1 is equal to, there are two forces, right? F, and there are also F and X, right? Oops, wrong color. Sorry. So if I set them equal to each other, so M1A system is equal to F minus Fnx, right? And if I solve for Fnx, right, I simply, you know what these are, right? So here we have 2.3 times 0.914 is equal to 3.2 minus Fnx. So we could solve for Fnx. And guess what? It comes out to 1.1 newtons. 3.2 minus 2.1, 1.1. So yeah, they pretty much are exactly the same. Okay. So this is part A. Now, if I were to push from, instead of from the left towards the right, let's say I push from the right towards the left. Okay, so for part B, show that if the same force F is applied to M2 rather than to M1, the force of contact between the block is 2.1 newtons, not 1.1, which is not the same as the value derived in, right, A. Explain the difference. So we know now, okay, instead of pushing from the left towards the right, if we were to press M1, and what's pushing M1 is basically the same normal force that is applied on 1 by 2. So F normal X on 1 by 2. Okay? And if we were to look at M2, here I have my force F and my F and X on 2 by 1. And we could consider going left is the positive direction because that's the direction of motion. Or you could just leave it, same up there, but let's just change it up a bit. Okay? So, why is this Fnx greater than if I were to push from the other side originally? Well, let's take a look. So here, if I were to do, again, if I were to do acceleration of the system, it's not going to be any different than what we already calculated to be, which is 0.914, right? Except it's going to go towards the left. And we consider the left direction to be positive in this case. If you still make this positive, just make this negative and things should still work out. Okay? So sum of all forces 1 is equal to M1A system, and sum of all force 1 is equal to just Fnx. Okay? So M1A is equal to Fnx. M1 is 2.3, A 0.914 is equal to Fnx. So my Fnx is equal to 2.1 newtons. And if I do this, it's still going to come out to be 2.1 newtons, believe me. But why is it greater when you push from the other way than when you push from the more massive side? I like to think of this in more extreme cases. Okay, let's think about what happens if I had my quantum observer here between the blocks, right? Now this quantum observer is going to feel some pain depending on which way this thing is going to be pushed. Let's say this mass 1, instead of being only 2.3 kilograms, let's say this mass 1 is a solid granite block that has like 40 metric tons of mass. Okay? And this M2, let's say it is made up of the space shuttle tile that's very, very light but very strong, right? And this mass is only like 3 kilograms. The quantum observer in here, depending on which way the force is applied, it's going to feel different forces. If we apply the force here with 400 elephants pushing on this thing, this will accelerate, let's say, with 0.9 or 1 meter per second squared. Well, he's going to be pushed by the granite with acceleration of 1 meter per second squared, and he only has to move this 10 kilogram block this way, so he's not going to feel as much pain. However, if 400 elephants are pushing this direction, this is crushing this quantum observer against this granite, and because it has to push with such a greater force to move this and to accelerate at 1 meter per second, the force that quantum observer feels is going to be enormous pain. So the force has to be much greater to accelerate that solid 40 metric tons of granite. So he's going to get crushed. You get the point? So take it to the extreme cases and you'll see it a lot more clearly why it's much bigger pushing this way than this way. Is that good enough explanation, everyone? All right, so visualize that, and I think it helps. All right, any questions? All right. I think that's the time, right? Is it over at 9:30 today? Yeah, I think so. So listen, I'm gonna stop my